if A is a subset of B union C and B is a subset of A union C, then is C a subset of A union B? Well, to figure out whether or not the statement is true, let's draw a diagram. So in our diagram, let's draw the two conditions we're assuming to be true, and that is A is a subset of B union C and B is a subset of A union C. So first let's tackle what this means over here. For A to be a subset of B union C, it means everything in A has to be in either B or it has to be in C. This means that no part of A can not be in B or in C, which means A has to either be here or A has to be here, which means we cannot have this region right here. Let me actually highlight it maybe in a different color. And to make it more clear, we say cannot have for A to be a subset of B union C. So we want to remove basically this area I've shaded in orange. Okay, what about B being a subset of A union C? Well, it means all of B has to be either in A or it has to be in C. So for the moment, forget about this orange part we're removing. Forget about that for the moment when we're focusing on this. When we're looking at this, we want to say, well, no part of B can be not in A and not in C. It means it has to either be in A or in C. Well, that means we cannot have any part of B, like so, that is not going to be in A or C, right? This part, if we again forget about this orange part, means B has to be in A or it has to be in C. Fantastic. So, more clearly, cannot have for B to be a subset of A union C. Fantastic. Okay, so now that we see these two conditions to be true, can we look at C and see, well, is C going to be entirely within A union B? Is C going to be entirely in A or B? And the answer is no, right? We have this section of C that is not in A and it's not in B, right? So that means that this statement must be false because we found C, elements in C, any element that is going to be in this part of C is not going to be in A or in B, or in both. There we go, we've proven that not all of C is going to be in A or in B, so this statement is going to be false. So to prove that this statement is false, we have to instead prove its negation. So what is going to be the negation of this statement? Well, we know that this is going to be a for all because even though I'm not saying it's for all, we know that because we have no restrictions on the sets A, B, and C, it's going to be for any sets A, B, and C, which means it's a for all statement. So what is going to be the negation of this for all statement? It's going to be a there exists. So it's going to be that there exist sets A, B, and C where this is true and this is true, but C is not a subset of A union B. Or, in words, it would look like this. So to prove this is false, we need to prove that this orange statement is in fact going to be true. And how are we going to do this? Well, that means we have to come up with exact examples of A, B, and C that will follow this rule, that will follow the orange statement. So how are we going to come up with sets A, B, and C? Well, let's have a look. What does it mean for these two conditions to be true? Well, as we saw, it means that we can't have this region exist, so we can erase this. And we can't have this region exist, so we can erase this. So it means that our set ends up looking something like this, right? So all we need to do is come up with a set C where there's going to be elements in C that are not in A or B. What is the simplest example we can think of? Let's think about that. Maybe we can say A and B are the empty set? No, because... No, yeah, we can say A and B is the empty set, because then the empty set is a subset of anything, and the empty set is a subset of anything. But then if C has, let's say, the element 1, 1 will not be a subset of the empty set. Yeah, okay, that should work. If we make A and B the empty sets, and we give C an element, it means that this is true because the empty set is a subset of any set, the empty set is a subset of any set, but the union of two empty sets is just the empty set, which means that C has an element. An element cannot be, and a set with elements cannot be a subset of the empty set because there's elements in here, but this empty set doesn't have elements. So I think that will be a fantastic example for this. So what do we say? We say, for example, let A equal B equal the empty set. Fantastic. Then B, or we'll start with A. I'll justify. I'll say A is a subset of B union C since the empty set is a subset of the empty set unioned with, I made a mistake. I didn't define my C. So you want to say A is equal to B is equal to the empty set, or you can just say is that A is equal to the empty set and B is equal to the empty set. And C we'll say is equal to the set containing 1. Then we can say A is a subset of B union C since the empty set is a subset of the empty set unioned with the set containing 1. Fantastic. And similarly, B is going to be a subset of A union C since the empty set is a subset of the empty set unioned with the set containing 1. And then we can say, however, so we've shown that this is true and that is true. Now we need to show this is true. So we say, however, C is not a subset of A union B because A union B is equal to the empty set unioned with the empty set, which is just equal to the empty set, but because that is equal to that, and given C contains the, we can just say given 1 is going to be an element of C, but 1 is not an element of the empty set, then C is not a subset of the empty set, making C not a subset of A union B. I think that works. However, C is not a subset of that because this is the empty set, and since 1 is in C, but 1 is not an element of the empty set, then C is not a subset of the empty set, which means C is not a subset of A union B. I think that's fine. Maybe there's a better way of wording this, but there we go. We can then say, therefore, the negation is true. That's our orange statement, meaning the original statement is false. I think that's readable for the most part. So there we go. We've proven that this statement is not in fact going to be true.